How do you use a motor in an environment which a typical motor just isn't designed for? Say in seawater, or an ultra-high vacuum perhaps, or when you need to completely physically separate an assembly, tool, or pump from the motor driving it, perhaps to control contamination, heat, or some type of noise. If this sparks your curiosity, then I suggest you stick around, as we're going to be designing, building, and testing a 3D printed magnetic gear transmission, a bit like this, where the teeth mesh using magnetism that can be physically separated from one another by a wall or even a hull. And we'll even see if we can get some more power out of it by adding a single solitary extra part. Hi, if you're new to this channel, I'm Ben and this is Design to Make. If making cool stuff and engineering things interest you, then you might want to click below to subscribe. Okay, so how does a magnetic gear work? It's made from three parts, an inner magnetic rotor, magnetic field concentrator, made from a soft magnetic material like iron, and an outer magnetic rotor. As the inner rotator rotates, it changes how strongly the outer rotor is attracted or repelled from the adjacent concentrator nodes. Here I've included a simplified version of the magnetization of the magnets and the effective magnetization of the concentrator node, where north is red and south is blue. The black arrows are the points of significant attraction, with one completely aligned north to south and two fairly well aligned to reach the lowest energy state. As I move the inner magnet 1/5 of revolution to align with the next concentrator, the outer magnetic ring moves in the opposite direction. And once again, there is one pair completely aligned north to south and two fairly well aligned. I can see that if I rotate the inner magnetic rotor one turn, it only rotates the outer ring 90 degrees, or a quarter of a turn. And I have to turn the inner magnetic rotor 4 revolutions to make this little guy get back to where he started, meaning this gear has a gearing of 4:1. So by changing the number of magnetic pole pairs on the inner and outer rotors, you can adjust the gear ratio by dividing the outer number of pole pairs by the inner number of pole pairs. Here I have 4 pole pairs on the outer and 1 on the inner, and the number of concentrators is the number of outer poles plus the number of inner pole pairs. So that's 4 plus 1, which equals 5. Let's take a look at how the magnetic gear is assembled in Fusion 360. Let's remove the sectional view to see the whole model and then build it up from the inner to outer components. Firstly, here is the 2-pole neodymium magnet with a hole in the middle, and most importantly, it is diametrically magnetized across its diameter rather than its length. Next are the magnetic bushings to locate the bearing in green. These sit inside the stationary magnetic field concentrator ring, where the soft iron is added to the rectangular channels. These and the inner magnetic rotor are fixed in place with a retainer ring and screws. Over the field concentrator fits the outer magnetic rotor with bearings either end and a green retainer plate to locate it in the correct position. If we look at a cross-section of the assembled magnetic gear, we can see how all the components fit together. Here is the inner magnet, the bushings, the inner bearings, all sitting within the stationary concentrator ring. The inner retainer, outer rotor bearings, holding the upper magnetic rotor and end cap. Here you can see quite well that the outer rotor is completely separated from the inner rotor by the magnetic concentrator. Okay, so now we've got the design done, let's print out the parts. I'm using 2 Core XY printers in parallel to make light work at this. And there we go. That was fast. And here it is assembled. Wow, I'm really motoring today. As you can see, it works. And I'm very pleased with that. To test the magnetic gear, I've designed a simple mount for the DC motor that will hold the magnetic gear securely above the table. There is also a 5 to 4 mm shaft coupling as well that you can't see to link the motor to the magnetic gear. For fun, I created a propeller to try, as well as a heliacally grooved drum to get an idea of the gear's maximum torque at different speeds. Okay, as before, now we've got the design done, let's print out the parts. Oh, and here it is assembled. Wow, I really am motoring today. As you can see, it works. I guess you could say I'm on a roll. The setup involves connecting the motor to a variable DC current. Here we connect the DC power supply to the terminals of the DC motor, supply both voltage and current to give us overall wattage measured here. So the idea is add a weight to the end of this string and start the motor up. It's able to lift the weight. I can calculate the effective torque being transmitted through the gear. We'll start small and work our way up. Let's get testing. Here we go. First, a dry one with a 5 gram bearing weight. The distance from the center of the motor to the outside surface of the torque jump is 5 centimeters, so the effective torque is 5 times 0.05 kilograms, which equals 0.025 kilogram centimeters, or converting to Newton centimeters by multiplying by 9.81 gives us 0.25 Newton centimeters. Next, we'll increase the current to 2.7 amps and add one large bearing which weighs 75 grams to the total weight. So the effective torque is 5 times 0.08 kilograms, or 0.4 kilogram centimeters, or converting to Newton centimeters is 3.9 Newton centimeters. Okay, going to two bearings, again weighing 75 grams. The effective torque is 5 times 0.155 kilograms, or 0.8 kilogram centimeters, or 7.6 Newton centimeters. This seems to be going fine. Let's add another bearing, which takes the torque to 1.2 kilogram centimeters, or 11.3 Newton centimeters. So it still seems to be going strong. Let's go to 4. Adding another large bearing, which increases the torque to 1.5 kilogram centimeters, or 50 Newton centimeters. Okay, that was close, but let's have a go at one more and take it to 5 bearings. That will give us a torque of 1.9 kilogram centimeters, or 18.6 Newton meters. Oh dear, that seems to have done it. Let's try the experiment again with a higher current of 3 amps. 1. Easy. 2. Also easy. 3. Still going strong. 4. Oh no. At the higher current, it seems to be too much for the 4 bearing. 2.7 amps seems to be right on the limit of the torque that could be generated by the gear. So the maximum torque of this gear is close to 15 Newton centimeters, or in SI units, 0.1 Newton meters. Okay, so can I make it any better? To try to improve the magnetic gear, I'm going to try to make the current outer magnets channel more magnetic flux through the concentrator by giving the field lines on the opposite face an easier path to the poles of the adjacent magnets by wrapping some magnetic material with a high magnetic permeability to the outer face of the magnets. The best I could find easily was some 0.8mm low carbon mild steel plate from Amazon, which I cut into 30mm strips. Then I used the wire bender I previously built to roll the plate into a circle. Then trimmed it to the correct length using the hardened steel wire cutters I bought for the wire raceways in the cross-roller bearing video. It's very satisfying when you can reuse tools in unexpected ways to get a job done. Here's the roll sheet inside of the outer magnetic rotor. Let's test it. So exactly the same setup as before, however we'll try the higher motor current first of 3 amps. One large bearing. No problem. 2 bearings, also easy. 3 bearings, still going strong. 4 bearings. Seems okay. Remember, this was the maximum current we could lift without the metal insert at the lower 2.7 amp current, but not at 3 amps, equating to a total torque of around 15 Newton centimeters. Okay, so moment of truth. Can it lift 5 bearings? Well, there we go. It can, which corresponds to a torque of 1.9 kilogram centimeters, or 18.6 Newton centimeters. Let's optimistically try 6 bearings, which would equate to a torque of 2.3 kilogram centimeters, or 0.22 Newton centimeters. Oh, no, that seems to have done it. We appear to have found the maximum torque to be between 18.9 and 22.3 Newton centimeters, or in SI units between 0.9 Newton meters and 0.22 Newton meters, which is an improvement of between 25 and 45%, which I hope you'll agree is pretty impressive. I think if I could increase the thickness of the metal insert, or used a material with a high magnetic permeability like permalloy or high purity iron, or perhaps use thin iron laminations like the ones you find in a transformer in the concentrator layer to reduce eddy currents, we might be able to increase the torque even further. Please do pop a comment below if this is something you'd be interested in seeing another video on in the future. So we know how much torque the gear can output, but how much power can it output? As I mentioned earlier, I've printed a simple propeller attachment to test this. So the plan is to measure the watts consumed at different voltages. This motor is designed to work between 12 and 36 volts, so I think we'll try 12, 24 and 36 volts for reference. The no-load speed spindle RPM at these voltages should be between about 2,000 and 9,000 RPM. So this is approximate as I don't know what the efficiency of the gear is working at, but given it doesn't seem to be getting particularly hot during testing, I'm going to estimate it's about 80%. So whatever number we're seeing on the display, we should be multiplying it by 80% to get an estimate of the output power. "36 volts streaming around 180 watts, giving us an output of around 150 watts. I don't think this is reaching the maximum output power, but to test that I would need a bigger propeller or faster motor. But for now, I'm going to work on the basis that it can output around 200 watts, which looking at the literature, would equate to around 1.2 to 1.5 kilograms of thrust in air given an optimized propeller design. Not bad.